Thank you. All right, so first I want to thank the organizers for accommodating my talk. I know it's a little bit in the not appropriate time, but I'll be gone tomorrow, so if you have any questions, do talk to me today. So I was thinking what would be interesting to share with the group today, and I thought that it would be cool to explore the link between the cosmic web and the small-scale clustering, which is particularly interesting in light of upcoming experiments, stage 4 and stage 5, which is kind of where my interest lies. So first of all, you might want to just ask, okay, why should we even care about these small-scale clustering analyses? Don't we already have all of the information we want in the large scales? And that might be the case, at least to some extent, but we know that the small scales also contain some useful cosmological and astrophysical information. So for example, if we look at the tension with Planck for the S sigma 8 constraints, a lot of these points actually come from exactly these small scale comparisons. And it's still a tension that is not fully understood, and it's an interesting thing to study, especially because these small scales contain a lot of the sort of inflowing velocity information that can be informative about the lambda CDM model, but also beyond that for testing general relativity and so on. And additionally, there are also like things that one might be interested in, like cosmic web interactions with the galaxies, or galaxy formation and evolution. And so in particular, I work with the DESI collaboration on these kind of small scale analyses. And just want to mention that, you know, DESI has already gathered more spectra than any of the previous surveys combined. So we have these exquisite measurements of very small scale clustering that we should really try to understand well and extract cosmological information from. And so the two types of galaxies that I will mention in this talk today are ELGs and LRGs, which stand for emission line galaxies and luminous red galaxies. And you can think of them as just sort of blue and red galaxies. So what is the current state of affairs? How do we actually perform this analysis right now? Essentially, on small scales, we are kind of stranded to use numerical methods, because analytical solutions, such as, for example, effective field theory, break down at these very small scales. Although I do want to just open a bracket here that there are some recent developments in the realm of hybrids between effective field theory and numerical simulations that I think are actually really exciting, and they allow us to probe slightly smaller scales. But for the most part, it actually, we really kind of need to use n-body simulations. They provide us nonlinear clustering. They're faster than hydro simulations. But the downside is that we need to come up with some galaxy population heuristic. And so to those of you who are familiar, this will be kind of review, but the most popular way of actually populating these simulations and then comparing them with observations is the so-called halo occupation distribution model, or the HOD model, in which the sort of simplest assumption is that to first order, the properties of the galaxies are dictated by the properties of their dark matter hosts. And in the even simplest version of that, which is quite ubiquitously used, we can say that the number of galaxies is dictated by the mass of the host halo. And I just want to draw a parallel here with the idea that Christophe Pichon had from yesterday about, you know, this really is an example of a model that kind of considers these halos as perfectly spherical cows. And maybe that's not the right thing to do, as I will try to argue. Okay, so this is the sort of typical plots that we look at. These are the mean halo occupation as a function of halo mass. And typically we say, okay, so at some mass of, say, 10 to the 14, we see that we are guaranteed to have a central for this particular tracer that I'm showing here, which happens to be red galaxies. And I am likely to get, on average, about 2 satellites. So this is the sort of like, you know, simplest way of generating these galaxy populations. Okay, and so the line of sort of work that I'm gonna mention to you today is about testing the galaxy halo model using state-of-the-art hydro simulations. And just want to introduce in this one slide the new Millennium TNG project that you may or may not have heard about. It's led by, again, Volker Springel and also Lars and several people on different continents. This is essentially an update of the illustrious TNG project. So this is larger box, factor of 15 in volume, has better large-scale statistics as a result, and more cosmological observables. So really kind of trying to make this bridge between galaxy formation simulations and really cosmological simulations. This will be available in 2024, but there are ways to actually make use of the data even now. So if you are interested, do either talk to me or you can email Volker. Okay, so the two papers that I kind of have put out as part of this Millennium TNG project are related to the 1 and the 2 halo term. And here I just want to summarize what is the sort of logic of my work. So, okay, first of all, we need to make an assumption that Millennium TNG provides us a plausible reality of our universe. And that doesn't mean that everything that comes out of it is the truth, but at least to first approximation, we believe that the gas dynamics make sense, and that, you know, the connection between galaxies and dark matter, at least to first order, is giving us something plausible. Okay, and then the next thing that we do is we're now going to take the dark matter only version of that simulation, and we're going to populate it using one of these galaxy halo models with galaxies and make a comparison between the two. So on one hand, we have this realistic-ish, you know, model of the universe via a hydro simulation, and on the other hand, we have this simplistic model. And so we're going to compare observable statistics, which for the most part of these surveys would be something like correlation functions. And if we find a discrepancy, then we should really kind of be worried, because, you know, if we analyze data with these models, then we're going to find some bias on our inferred cosmological parameters. So basically, if in my case, if I find a discrepancy, then what I do is I just try to come up with some heuristic that actually gives me a better comparison between the galaxy halo model and the hydrodynamical simulation. And then I try to sell it to people who are actually, you know, fitting it to data. So for example, right now, we have implemented a bunch of these findings into the DESI pipeline, and indeed it's giving us better fits to real data. So I'm going to say a few words about that as well. Okay, and so this is just a sort of, I'm just going to show here the simplest result from applying the mass-only HOD. So this was the simplest assumption you can come up with, where you apply that to the n-body simulation, to the dark matter-only version of Millennium TNG, and you compare it in terms of the clustering statistics. And you find that now your prediction, which is the dashed line, compared with the solid lines, is about 10% lower. And so that's a pretty substantial failure of that model. It implies that we can get like bias on large scales or bias in the inferred parameters of that same order. And and so this finding actually holds true for a bunch of different tracers at a bunch of different redshifts and number densities. So it's important to address it in some way. And the name of that effect is galaxy assembly bias, which, as was discussed yesterday, is a little bit of a confusing term. Okay, and so, all right, so, by the way, this result is kind of a recap of my previous work, so that's why I'm going rather quickly over it. But, so where does this 10% difference come from? So it turns out that the picture that I was describing with the mean halo occupations is kind of simplified, obviously. In reality, we have a scatter. It's not just a perfectly, well-known thing. And the scatter actually depends on additional halo properties apart from mass. So what people have been historically studying are these things like formation time, concentration, and velocity dispersion. And while I do think that some of them help out in reconciling these differences, in sort of my earlier work from my PhD, I showed that none of these internal properties can actually fully alleviate the tension. And so that's where the cosmic web comes in. So I will claim, and I will try to show in the next few minutes, that the surroundings of the halo, and in particular things related to the anisotropic pulling due to nearby structures, affect the galaxy formation and thus the clustering. Okay, so what do I mean by anisotropic pulling? Let's come up with some way of measuring that or quantifying that. So a very kind of convenient way of quantifying that is to look at the tidal tensor, get its eigenvalues, and compute something that looks like the equation over there, which essentially tells us how much anisotropic pulling there is locally at each location in your simulation, or say at the center of halo locations. And here I got inspired yesterday by the eigenvalue plots, so I'm also showing my own eigenvalue plots. But of course, in my case, I do that in 3 dimensions. So this is just for display. And you do that over some smoothing, which should typically cover your halo. You don't want to be too sensitive to what happens inside of the halo. You want to capture more of the large scale statistics or large scale structure effects. Okay, and so all right. So what happens if we now put that parameter in some way into our galaxy halo model? And I can give you details of how that's done, but I don't think it's that interesting. The bottom line is that there is a simple way of actually inputting additional dependencies into your HOD model. And if you do that, then you now get this new dotted line that is showing what the shear enhancement does to your prediction. So you can see that now on large scales, which is the goal of these clustering kind of studies, is fully reconciled. So that is particularly interesting, especially for blue galaxies, which have so far been understudied, but are becoming more and more important with Euclid and DESI and so on. And previously we showed that this holds true also for red galaxies in real data. So here I'm just highlighting the Yuan et al. Result from 2021, where we showed that actually there is this tension known as the lensing is low tension in CMAS data, where one cannot fit simultaneously the galaxy lensing and the galaxy-galaxy clustering. And so we showed that if you actually incorporate these density dependence into your galaxy halo model, then you can cut down this tension by about 50%. And we're, in fact, actually hoping that this updated definition of the environmental dependence, which now takes into account the shear, will give us an even better result, because shear is even more sensitive. And again, this is from yesterday. So shear, the way we define it with the gravitational potential, is even more sensitive to your large-scale surroundings. And it turns out that, at least for blue galaxies, that really turns out to matter a lot. So if you're interested in more details, do talk to me. But the bottom line is that we really find this evidence for two-halo conformity. So especially for blue galaxies, we find that their luminosities are correlated on pretty large scales, and shear sort of, or the presence of large-scale structures nearby is really a good indicator of what their distribution looks like. And so here I just want to digress for a moment about and say a few more words about this galaxy conformity. So in the second work, which is on the one halo term, we also show that there is indication for conformity on even shorter radii or shorter displacements. And 3 main results I'm just going to highlight here are that we find that blue galaxies are not radially distributed within the halo. They exhibit superposed occupations, and that there is a codependence between the centrals and satellites. And the hypothesis is that the collapse of porous structures into filaments and walls will result in an increase in the pressure, and hence an increase in the galaxy formation. And And I want to say that this is something that is not just the case in simulations. What I'm showing on the right is actually preliminary results from DESI. So the measurements here, the orange line, are the true measurements, and then the several lines are showing what happens if you fit with and without these conformity parameters. And in fact, we can see that, for example, the blue line here, which is just a more or less a vanilla version of the halo model, aka without any conformity, is really not a very good fit to the data. But once we include conformity in the blue line, we really kind of capture this uptake on small scales in the ELG clustering. Okay, and so going back to the cosmic web in slightly larger scales. So an interesting exercise that we can do is we can take the galaxies and split them into the different components of the cosmic web. So galaxies that belong to peaks, filaments, sheets, and voids. In my case, I don't have any galaxies in the voids because I'm looking at fairly massive objects. And basically, you can shuffle now the halo occupations within each of these different environments. And what you will find is that now the clustering is consistent. So this is showing the ratio of the true clustering of the hydro simulation with the clustering from the galaxy halo model. So in some way, this is again indicating that the cosmic web is really a predictor of the galaxy properties that we find. Okay, and so I just also want to kind of draw another parallel with the talks from yesterday. So Tom was talking about the KNN statistics, and I also, in the context of cosmology, but I also want to argue that it's helpful in the context of these galaxy assembly bias kind of studies. And so here, for example, I'm showing that if we take basically our galaxy distributions and measure the KNN statistics, that gives us additional information. So essentially, you can find that that two models give you very much the same 2-point correlation function, but give you very different KNN statistics. And that's another way of essentially adding more information about your galaxy distribution and refining these models, because at the end of the day, we don't just care about the 2-point clustering, we care about the full galaxy distribution. And so, as Tom mentioned, there's currently ongoing work on applications to DESI data with light cone emulators and on Abacus Summit that I'm involved with, if you're interested in hearing more about that. Okay, so I think I'm maybe 1 minute early, but so let me summarize about what I just talked about. So essentially, the galaxy formation is affected by both known local effects, it seems. So it's not correct to assume that halos exist in isolation. We need to take into account the broader context of their surroundings. There are non-gravitational effects that are contributing, so it's not just the dark matter structures that are gonna play a role into the kind of galaxies that form and evolve inside of these halos. There is also an effect that's purely related to the baryon funneling through filaments. There is also then for ELG specifically, which is the sort of more new finding, as I mentioned, we find that they have galaxy conformity on very large scales, and that seems to echo what we find in preliminary data from DESI. So accounting for these effects of the surroundings would be quite important. And alternative statistics such as KNNs can help us further improve our models. And yeah, so I wanted to just say again that it's a pleasure to be here. And if you want to, I'm also happy to chat about some of the other things I'm involved with, such as intrinsic alignments, work with Millennium TNG, the Sunyaev-Zuldovich effect and the dependence on environment, hybrid effective field theory, and Zuldovich approximation control variates, which I think are relevant to this conference. So do let me know if you're curious about any of them. Yeah, I'll see you online, I guess. Thank you.
Thank you, Boryana. Questions?
Yeah.
Thank you for a talk, a great talk that I obviously subscribe to. What did you actually mean when you modeled the tiles? Did you use some of its eigenvalues, or did you use the vectors, or both? Or
for the title, this one.
So, okay, you use QR, this quantity, okay.
Mm-hmm.
And did you look at the how do you call it, conformity? The conformity business, I forgot what the term is.
Yeah,
did you look at it in terms of anisotropy, so that it's different in different direction, or did you?
A little bit, yeah, very little, and only on the one halo side of things. So I haven't looked at it on the sort of broader, large-scale structure. Like, for example, alignments with filaments would be something else to look into.
Okay.
Yeah.
This is the same that other people called alpha. It's like
I think so. I've seen it as alpha. Yeah. It's just the eigenvalues of the tidal tensor. Yeah.
So going from this slide to the next slide, right?
Mm-hmm.
I guess you kind of obviously you skipped over the details, but basically you went into the simulation, you computed those quantities from the simulation particles.
Exactly.
And then you computed this correction.
Exactly, yeah.
So is your plan to just apply this correction onto the real data, or are you deriving functional forms to
yeah, so that's a good point. All right, so basically the way that we do this is you take a dark matter only simulation and you now measure these quantities as you mentioned. You construct some kind of, new galaxy halo model that takes it into account in some form. So, for example, you can have a two-dimensional HOD that has mass on one hand and shear on the other hand. That's kind of a simplistic way of thinking about it. And now you can vary the various nuisance parameters in your model and generate different predictions about the galaxy clustering. And so once you do that, you can compare it at that level with the data. So we don't do anything to the data. At the end of the day, we're just comparing statistics of the real data with statistics from your simulation, where you have dressed up your simulation with various things like fiber collisions and, and mass, blah, 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 and redshift evolution and all of that. So, yeah. Does that help? Yeah, okay, cool, yeah.
I guess I'm going to get you to a previous slide again.
Yeah, which one?
So just the previous one.
Okay.
When you think, so in terms of dynamics, what matters is actually the tidal tensor in the initial conditions, and because you can measure that in the simulation. Have you tried doing the HOD instead of measuring the tidal tensor in the evolved universe, do it in the initial conditions?
Yes, I have not tried that.
So, I mean, it would not be practical for survey, but just like to see whether you get more information by doing that.
I'm curious. I don't think that it would be a problem to do this analysis on the survey too, in the sense that, again, like as I was explaining, we don't actually ever do anything to the survey. We're always just taking simulations and forward modeling them to make them look like the survey. So you can do whatever you want as long as you can measure that property in the simulation. So I'll be curious if that works. I mean, this kind of goes back to the EFT kind of approach of things. And indeed, that's a direction that I've always been curious about, but haven't really explored. Yeah, thank you.
Yep. And I have a small follow-up question. You can also think that, for example, the formation time is also going to be impacted. Well, it's going to be a relevant parameter, which somehow like ties back again to the tidal tensor, but on a different scale. Like, have you tried looking at the tidal tensor not on one scale, but at one or two scales, and is it even doable with the amount of data that you have?
Sorry. Is your question?
So essentially, when you do HOD, you have like mass on one axis, and then, for example, tidal tensor or second axis defined on some scale. Have you tried looking at the tidal tensor at two different scales?
Different physical scales, right?
Yeah.
Oh, yes. Yeah, that we have. Yes. I thought you said like redshift, but yeah. So we have looked at different physical scales, like different. As I mentioned, there is a smoothing here, like this R smoothing. turns out that you're trying to just find, you know, where you're the most sensitive, and that happens to be a little bit over your halo radius. But even if you go to even larger smoothings, you still pick up a bunch of that signal. So sort of my earlier thoughts about this were that it's related to the splashback radius. So the idea that actually what we call the halo and its radius is kind of made up. But it seems like, at least for ELGs, there is stuff that's happening on even larger scales than that. So things that are related to quenching of due to large clusters and so on.
Right.
Yeah.
Sorry, I had a question before. Related to the detail of how you put in the shear components into the modeling of HOD, you demonstrate with the Millennium TMG data that this does exactly the job to correct for the offset of 10%. Yet, if I remember correctly, the clustering analysis out of the Millennium TMG paper show that the color dependence of clustering isn't great.
The color? Or?
Well, when you separate the galaxies into different colors, the color dependence of clustering, if I remember correctly, isn't particularly great. So I wonder if this would potentially be a concern. To what extent the shear component being introduced, is it a fixed quantity or is it some free flow parameter that you can adjust when you apply this to real data?
Right. Okay. So that's a very good question. So, okay. So in some sense, you're saying, okay, if your simulation is imperfect and not converges well, your colors are off, your star formation is off, what happens? So yeah. So first of all, the way that I select ELGs and LRGs doesn't really depend on exactly what the values of the colors are. I'm just selecting it by abundance matching the star formation rate and so on. And yet that can have its own issues. So when we analyze data, we never take a true value for the shear parameter. That's always a nuisance parameter that you're marginalizing over. So in some sense, you have some freedom as long as shear is actually something that physically happens in the universe. Yeah.
I'm a great fan of tide as a quote-unquote assembly bias extra parameter. But one of the things that I would like to see is a better HOD. Namely, the distribution of different kinds of galaxies within a halo depends upon the type of galaxy. And you presumably have the data, at least at a simulation level for this. Have you tried that so that you don't just put them down in, you know, the mass uniform Poissonian manner?
Yes, to some extent, right? So do you mean like radially, whether we put it radially?
Yeah. For example, some will be more centrally concentrated, and so you don't want a response function which is uniform, which is what everybody does for HOD, or at least most people assume there's more sophistication out there somewhere. But you have sophistication here, so you should be able to
I have
do
some
it.
sophistication. I don't have the time for maybe enough sophistication, but no, that is something that we kind of looked into here when I was saying about the digression. So one of the things was that we find that LRGs really kind of follow more or less this NFW profile distribution with some, you can assume basically that they're isotropically distributed, and you wouldn't be too far off from the one halo prediction of the simulation. But in the case of blue galaxies, because of this argument of conformity, you actually find that they tend to be very closely clustered. So if you look at, you know, that one ELG, one blue galaxy inside of your halo, you're much more likely to find another one right next to it, rather than isotropically somewhere in that halo.
But in terms of relative to the standard HOD, there is a distribution, and for the bluer ones, it should be more on the edge than in the core. So it would be great to have fitting functions for that.
Right.
Because I don't think it's been well done.
Right.
In literature.
Yeah. In that paper, there's some, you can look at the radial distributions and so on, and velocity distributions of the galaxies. We have not done fittings, but yeah, that would be something to do. Yeah, thank you.
So I guess now that the questions are done, it's time for my rant, which is, I often twitch when I listen to large-scale structure cosmology talks, because in the practice is basically for each galaxy you retain 3 numbers, which is the XY, RA, and DEC and redshift, and basically throw away 95% of all the information. In other words, the spectrum, and also you retain. Actually, you also have the image of the galaxy. So I guess my rant as a grizzled old person is that I think the next step is to try and fold in the information in the spectrum. Like what other dependent variables might be in the spectrum. You even have the morphology in the image, and I suspect that all that information will go quite a bit beyond this kind of HOD modeling.
Yeah, no, that's totally true. Yeah, it's something that is, I think, ongoing work, but unfortunately it probably involves machine learning, which people are quite allergic to in the cosmological world, but yeah. At least in the observational side of things. Yeah.
Any other questions? Well, if not, let's thank Boryana again.
Yeah, thank you.
And actually, let's thank all our morning speakers for excellent talks. And we'll break for lunch and reconvene at 2 p.m. Thank you.